All right, guys, welcome to our Saturday edition of CCIE Routing and Switching. We are moving on into another major topic of OSPF, what we call stub areas. And actually what I've done is I've kind of combined these three lessons into a single lesson because I felt like there was a lot of overlap between these different lessons. So what we're going to be covering is kind of an introduction to OSPF stub areas to start. And that's going to be mostly kind of a lecture and kind of a discussion. And of course, I'll start to keep some notes. In fact, let me go ahead and launch my Notepad++. Let's see here. All right. So we'll be talking about OSPF stub areas. And then we're going to move into basically doing the configuration of our stub areas. We've got a topology here that we're going to be using that I built for this purpose. Kind of similar to the topology that we saw in the last lesson when we were talking about OSPF. Sorry, I got something in my mouth here for some reason. And it's not supposed to be there. Anyway, so we're going to have kind of a multi-area design here. We're going to be introducing two concepts, a stub area configuration, totally stubby, NSSA, and totally NSSA. And then finally, we're going to wrap up our lesson today by talking about traffic engineering with OSPF stub areas. Now, I know that this says this would end up being about 3.5 hours, but it's certainly not going to take that long. It could be about 2 hours, but you know, it's like I said, there's a lot of overlap between these topics. So rather than have three different lessons discussing this concept, I thought I would go ahead and try and combine everything together so we can make a little bit of progress here. We're of course not going to cut any of the subject matter out. We're still going to focus on a lot of the configurations and a lot of the details that you're going to need to know for the written exam and the lab exam. So let's start by talking about some of the basic concepts of stub areas. All right. And overall, the concepts are relatively simple. OSPF stub routing. In OSPF, we have a few choices when it comes to performing stub configurations. And the primary purposes of stub routing, the purpose is to scale OSPF. Right? We saw a similar concept in EIGRP when we had EIGRP stub routing configurations of, setting up, you know, stub summary, stub connected, and so on. But that was done on a per router basis, on a per interface basis, because EIGRP is distance vector and it's a flat domain. Because of our two-tiered architecture in OSPF, stub routing features are limited to specific types of routers and so on. So in this lesson, we're going to introductory lesson, lesson 37, we're going to start to talk about what is a stub area, what are the different variations. We're going to talk about the type 7 link state advertisements, what those look like, where we're going to see those type 7 LSAs within our topology. We're also going to talk about the scalability limitations that we have with OSPF, right? Like I said, in EIGRP, we do stub routing and stub summarization, or route summarization on a per interface basis and a per peer basis. So a router will advertise itself as a stub router in the hello packets with the stub flag set, and then we treat that router differently, not sending queries to the router and so on. But in OSPF, because there is a fixed hierarchy in OSPF, it's a little bit harder to scale. We have to maintain that two-tiered hierarchy where we have area 0, and then we have the other areas that are connected to area 0. In any event, scaling in OSPF is really a function of two things. All right. Number one is how complex is the topology graph that we are creating, right? And that would be basically you know, how many routers are there in, sorry guys, in an area. That's number one. You know, if we have a whole bunch of routers in an area, that is going to mean that we're going to have a very large flooding domain which means that we're going to have a lot of shortest path first runs and shortest path first calculations. So if we have a flat area 0, that means that as soon as there's a change in the topology, everyone in that topology has to calculate the shortest path first process, or go through the Dijkstra's algorithm and run the shortest path first algorithm. We could implement a feature called incremental SPF. We don't actually really talk about incremental SPF in this case. It's a function of OSPF where a router can actually make an independent decision of whether or not the SPF algorithm needs to be run based on whatever change occurs in the topology. But for the most part, and in most cases, this incremental OSPF SPF calculation is not really going to have much of an effect on convergence or the speed of convergence or the scalability of OSPF per se. Okay, so that is not something that we're going to take a look at. We're going to look at some more traditional methods of establishing scalability within OSPF. Now, the second thing that's going to affect the scalability of OSPF is how much reachability in the topology is there, right? So what does that mean? How much reachability information is there? And that really means how many routes are being advertised. How many routes are being advertised, all right? So I call this essentially the complexity of advertised, there we go. I simply refer to this as basically the complexity of OSPF, right? So this is essentially the size of the routing table, the routing information base, which is going to increase the size of our forwarding information base. So number one, how many routers are there in an area? We can, of course, limit that, but that's going to require more areas or kind of a more, complex design with regard to changing where the routers exist within the topology. And how many routes are being advertised is going to be really a function of whether or not we're creating those type 3 LSAs on the area border routers and the type 5s or type 7s on the ASBRs to summarize a lot of the prefixes that might be injected into OSPF, okay? So we'll talk about that. We'll take a look at that. We need to essentially, in order to scale OSPF, cut down on the topology graph. And basically, everything that we're going to talk about in this lesson, essentially, or these 3 lessons that are kind of combined together, is really how, minimizing these 2 variables within our OSPF database. All right. It's also important to understand that there's a big difference in OSPF, and this is not the way it is in EIGRP, but there's a big difference in OSPF between topology versus network layer reachability information. All right. So topology would be related to the first option. How many routers do we have in an individual area? And network layer reachability information could be affected by implementing things like route summarization. All right. So the idea of summarization, and we'll put this in, I'll put a couple notes in here. Topology summarization with regard to OSPF is, number one, we want to hide the details of what the graph looks like in other areas. That's really the primary goal. Now, if you recall from our discussion previously, type 1 LSAs will get propagated individually as type 3 LSAs, and they will not be summarized by default into the other areas. So this is something that we need to do as part of our configuration. We only want to run essentially the shortest path first algorithm for any intra-area destinations within the area. The problem is, by default, having multiple areas does not hide reachability information. All right? We just need to make sure, and this is what happens by default, that those type 1 LSAs are then going to be created as type 3 LSAs. So even though I may have an area that has 1,000 type 1 LSAs, by default that's going to generate 1,000 type 3 LSAs into the backbone area or other areas throughout the autonomous system. So we don't just have to create areas, because by default, areas are not going to hide reachability information. They just basically change the LSA type and how that route is identified. Okay, so network layer reachability information summarization is going to reduce the number of routes. We're going to take, for example, a lot of multiple longer match prefixes, and we're going to combine them into some sort of smaller or shorter prefix length by using the area range command. All right, I will try to demonstrate this concept, although it's not as critical as the special area type configuration. We will have, I think we've already had a little bit of discussion on how summarization works on not only the ABR, but also the ASBRs, using the summary address on the ASBR and the area range command on the ABR. So let's say, for example, that I want to, in fact, summarize information in my topology, right? So we can reduce the NLRI graph by performing summarization. Unfortunately, there's only 2 places this can be accomplished. And we did actually see this, I recall now that we saw this as part of our configuration previously. On the ABR, we use this area X range command to summarize from an area. And on the ASBR, we use the summary address command. All right, so those are the 2 places that we can reduce the size of this topology database by taking these longer prefixes and referencing them as simply a shorter prefix length. All right, the key distinction with OSPF topology is that we're doing this not on a per link basis, but within the area itself, because we're accomplishing these configurations on an ASBR or an ABR. All right, so we can do pre-prefix summarization, where I simply take 2 routes, for example. So prefix summarization. I might take, for example, let me spell that right. Say 10.0.0.0/16 and 10.1.0.0/16, and I would then summarize that to 10.0.0.0/15 as an example, which would include those 2 networks. And again, we could do that on the ASBR or the ABR. It's just a matter of what syntax we're using to create that summary. All right. Now, the other way that we can do this, and this is what this lesson is really all about, is to do per LSA summarization. And what per LSA summarization does for us, here, let me do this, per LSA summarization, is it allows us to change essentially how OSPF routers exchange information. So we would, for example, remove all inter-area routes and replace them with the shortest match routing, which is a fancy way of essentially saying default route. Or we could, oh, and by the way, that would be an example of a stub area, or perhaps a not so stubby area. The other option would be to remove all routes, external routes to the area, right? And again, replace them with shortest match routing as well. And there is obviously going to be a difference here. We'll talk about what that difference is. Let me get a copy of this here. We'll talk about what that difference is here in a minute, but this would be totally stub totally stubby, or totally not so stubby in that example. All right. So our path selection rules still don't change when we create stub areas. The path selection process will change because of the types of routes that we will see. All right. Now, what types of routes will actually enter an area are going to be completely dependent upon what type of stub routing we're going to create. All right. There are a couple of caveats to doing stub routing. Stub routing basic requirements include this. All right. And we'll get into the details of each of the stub routing configuration elements in a little bit, but area 0 can never be a special area type. All right, because it has to have that full graph of the entire topology. Also, we cannot create virtual links across a special area type. So if I do have a situation like we talked about last time, where we had in our last lesson, where we had a need to create these virtual links, we would not be able to create a virtual link across these special area types. Okay? There are essentially 4 types of special areas. And again, our goal here is to kind of describe these concepts, and then we'll start to take a look at the configuration and how it's affected with the actual database, and we'll take a look at some of those configuration components. All right. Stubby area. Some people simply refer to it as a stub area. I'll put that in caps. We'll just call it a stub. All right. And then we have totally stub. Let's be consistent here, though. If it's stubby, we'll call it stubby. Yeah, it depends on the documentation, whether or not you're going to see stubby or totally stubby, or stub versus stub, totally stub. And then we have a not so stubby area and not so totally stubby area. Again, that one you might see referenced as a totally not so stubby area, but technically it really should be not so totally stubby area if we're following the same logic. All right. How do these stub areas work? They filter traffic at the transit point in our topology. In fact, all of the filtering with these special area types is going to be enforced at the area border router. And the idea is that we are trying to limit what LSAs can actually enter the area in the configuration. We're not trying to limit what can leave the area. We're trying to limit what can enter the area. Type 3s, Type 4 LSAs, Type 5 LSAs will be filtered depending on the type of stub area that you create. The reachability information that we would normally see based on those LSA types, that's going to get removed, and it's going to get replaced with a default route in most cases. There's one instance where a default route will not be included automatically, and that has to do with whether or not we would want to use some sort of external default route or a default route coming in from the autonomous system within OSPF. All right. Also, stub configurations are part of the negotiation of the peering relationships between routers within the area. Unlike EIGRP, where we configure a single router as a stub, in OSPF, all the routers have to agree on the stub configuration. There's actually a stub flag that gets set in the hello packets, and all the routers have to agree on that stub flag. Okay, this is also done as part of the negotiation within the area. So if I configure a stub configuration on one router within the area, all the routers have to agree on what that stub configuration is going to look like. They don't have to be the exact same type of stub configuration. For example, on the area border router, you may configure that with a no summary option. and then you would not place the no summary option on any of the internal routers within the area, but they still have to agree on the fact that they are stub routers. Okay? So let's start by breaking down kind of what we call the logic, the logic that OSPF uses based on these different types. Here's the basic concept, and this is from the perspective of routers that are in the special area. I know how to get to my ABR, right? I'm going to use that SPT calculation with LSA type 1 to get to my ABR, because my ABR is part of the area. My ABR knows how to get to the ASBR in other areas. All right, now that could be done with a type 4 LSA, most likely, and of course the external routes are going to be represented by type 5 LSAs. I guess I should have mentioned here, prior to going into this concept of what's allowed and what's not allowed, or what we do and what we don't do, is a stubby area allows only type 3 LSAs to enter the area. A default route will be injected to represent the suppressed network layer reachability information to the suppressed type 5s. All right, so because type 5s are not allowed, because type 5s are not allowed, type 4s are not necessary. So we're going to be filtering out type 4s, we're going to be filtering out type 5s. So that means that we're not going to see any OI or OE1 or OE2 routes into this area. Okay? Now, again, going back to the logic here, I know how to get to my ABR because I'm using my type 1s within the area to get to my ABR. My ABR knows how to get to the ASBR in the other areas. So that logic, using this recursive concept, this recursive logic, if I can default to my ABR, I don't need the details for the external routes. All right? And that is essentially the basic logic that we're using in this case. I'm going to get the same result from just using default routing to get to my ABR, and then I have reachability beyond the ABR because of that recursive routing logic. So we do generate a default route in this case, and that's injected automatically, I should say, by the ABR to represent those external routes that are being suppressed. Okay? Now, if I extend this, just copy this, and I go into my totally stubby concept, we allow only a default route into the area. Okay? So in a totally stubby situation, I only allow a default route into the area. A default route will be injected automatically by the ABR to represent the suppressed type 3s and type 5s. So OIA or OE1 or OE2 is not going to be allowed in a totally stubby area. Because type 3s and type 5s are not allowed, well, of course, type 4s are still not going to be necessary, but the same logic applies in this particular case. I know how to get to my ABR. I'll use my shortest path tree process to get to my ABR with the LSA type 1. My ABR knows how to get to the area networks, which are my type 3s, and the ASBR in other areas, which are represented by type 4s and type 5s. For any routes, I should say, any routes outside of my area. All right, does that make sense? The concept here is that we usually only have kind of one way in and one way out of the area. The configuration design is always going to depend on what kind of topology you have, and that will change based on the topology. If I do have multiple exit points out of the area, and we'll actually take a look at that in our configuration, it does get a little bit more complicated. If you only have a single ABR, there is really no reason to have a stub area and not a totally stubby configuration, because you're only going to get to the external routes and the other type 3 LSAs the same way by using that default route to reach those destinations. All right, so what about the not so stubby logic? Well, in the case of not so stubby, we have a bit of a problem if, for example, we have some sort of router connected to an external system or an external domain like an extranet or whatever, and we need to be able to introduce those external routes by providing some sort of redistribution between the non-OSPF domain and the OSPF domain. Stub areas block external routes. So what do we do in this particular case? Well, in this particular case, we do filter exactly like a stubby area, with the exception that we can have an ASBR in the area. And if you recall from our previous discussion, an ASBR is any router that's going to redistribute routes from a non-OSPF process into the OSPF process. All right. Now, because this is defined as a not so stubby area, we're going to generate the ASBR in the area is going to generate type 7 LSAs. All right, which are NSSA external LSAs. All right, the ABR in that area will convert those type 7 LSAs to type 5 as they leave the area into area 0. So as far as everybody else is concerned, and by the way, the ABR is still going to generate the type 4s to represent the ASBR that's in the area. But as far as everybody else is concerned in the topology, these look just like external routes. All right, so we are going to send in the type 4s. We're going to send in the type 5s. I'm talking out of the area, not going into the area. But here's the biggest thing. Because not so stubby acts like stubby, all inbound type 3 or type 5 LSAs and type 4 LSAs are filtered. So you would hope in this case, in order for me inside this not so stubby area to be able to reach these destinations, that I would have some way of routing to these external routes. Very, very important here. I'll put a couple asterisks here because this is the only case where this doesn't occur. The ABR in this case does not introduce a default route into the special area by default. And you might think about that and say, well, that means I'm going to lose my NLRI information for those external routes, which is totally true. But there is a reason why this was done, right? In fact, it's really kind of an important point. The default route is something that you would certainly need if you want to reach those external networks. But in this case, we're trying to define whether or not we want the default route from OSPF or we want the default route to come in as a type 7 from the external router. What we would refer to, and a couple of people I've heard refer to it as hot potato versus cold potato routing. We are going to talk more about that when we get into some of the special traffic engineering concepts, not in today's lesson, but in our next lesson, we're going to talk about traffic engineering with not so stubby and totally not so stubby areas. All right. So is there anything else I need to mention about this NSSA? Nope, not really, because it's going to go ahead and take all of the properties of stubby and introduce those, but with the exception of that we can have an ASBR in the area. All right, so we do in this case filter for totally not so stubby, exactly like a totally stubby area, with the exception, again, that we can have an ASBR in the area. All right, probably could have just copied that, but basically you get the idea. All right. Now, a default route will be injected in this case, so we're going to go ahead and copy most of this information here. Well, I don't really need to copy it, but I will copy this line for sure, because again, unlike the previous example, the stubby, not so stubby area, with this totally not so stubby area, a default route is automatically injected by the ABR. All right, so we'll take all the properties of totally stubby, but we are going to go ahead and say that an ASBR is going to be able to generate type 7 LSAs. The ABR in that area is going to convert them to type 5s. And in this case, we'll go ahead and copy these lines here. All inbound type 3, type 5, and type 4 LSAs are filtered into the area. Okay? So these are the four special area types that you will see: stubby, totally stubby, not so stubby, and not so totally stubby, or what I usually refer to as totally not so stubby. It just sounds better off the tongue in OSPF. All right. Now, let's talk a little bit more about the type 7 LSAs. And we will actually get into this in even more detail later on because we're not going to focus a lot of attention in this lesson on the last two special area types. We're going to focus primarily on the first two special area types, although I will have to configure one of those last two just to demonstrate some of the concepts that we want to cover in this lesson. Is what is a type 7 LSA, which are called external NSSA routes. All right. They are flooded only within the area, as we mentioned before. They are changed to type 5 at the ABR when they leave the area. They describe essentially the external routes being redistributed. And they have a seed metric, which is a default of 20 actually, which is the standard for a cost of 20, which is the standard for any redistributed routes into OSPF. They have a special metric type, which defines how they show up within the area, either of either ON1 or ON2. And we will see what happens in that with that later on when we get into the configuration of NSSA and totally NSSA later on. All right. ON2 is the default, and it has to do with how the metrics are calculated once the route's been injected. I'll just mention it specifically here, and then we'll see this later on when we get into our next lesson in the configuration of these special area types. But type 2, not LSA type, but external type 2s, will not increment the metric as the traffic flows through the autonomous system. Whereas type 1s, external type 1s, the metric will be incremented per link as the information moves through the topology. All right. Now, there is a very important concept to type 2 LSAs, much like type 5s. What is the forwarding address? Right? This is a property or a value, and it's actually technically called the forward address. What is the value that gets placed into the LSA, which basically defines who I route towards to reach that destination. We'll talk a little bit more about that when we get into our traffic engineering section. Usually it's going to be the ASBR itself, but it could be somebody else in the topology in some designs that we actually see. In addition, you can also set a route tag on those routes as well. All right? All right. So that is the kind of introduction. I have a couple more things to talk about here before we start to get into the implementation, which is technically the next lesson, but we're going to go ahead and combine it here. And we're going to take a look at some of the databases and the configuration. The main thing about this entire conversation today, though, is that you understand what LSA types you will see in the topology based on your deployment models. All right? We will take a look at our configuration. We're going to also take a look at what happens if I have multiple routers, area border routers in an area. Only one router is actually going to translate the NSSA external routes to the type 5s. So we'll actually see that process. There's actually an election process that takes place to decide who's going to provide that translation. We only need to see one copy of those external routes. And we can actually set the forwarding address to some sort of non-zero value so that we can traffic engineer how we get to those external routes. It's important to understand that the OSPF state machine does have a very specific route selection process. All right, next I'm put it in the notes here, even though it's not directly related to what we're doing here. The route selection process, and we mentioned this in the last lesson, it's very specific. O routes are going to be preferred over OIA routes, which are my type 3s. Those are going to be preferred over OE1, which are my incrementing metric type 5 LSAs, versus OE2, which are my non-incrementing metric type 5 LSAs. Sorry, let me do N1. Always 1 is preferred over 2. OE2 versus ON2. So remember, my E's are my type 5s, my native type 5s. The N's are my native type 7s. So this is kind of that state machine process for selecting the routes. Now, it does actually get a little bit more complicated when you get into having multiple E's and multiple N's, because in some cases it might be longest match prefix routing. It could be metric-based routing. But the only use case that we have when we're trying to deal with these different path selection options is if we have multiple ABRs in a special area type. I intentionally configured that in our topology so that we could see some of that behavior, and we'll continue with that discussion in our next lesson as well. All right? So let's go ahead and jump into the configuration. All right? Let's take a look at our topology first and see what it looks like just using a normal configuration. So here is my topology, already fully converged. The only thing that I'm not doing in this particular case is I'm not redistributing routes from R4. So that's going to be my first step. I'm going to go ahead and redistribute my routes from R4 in both directions, so that we have, you know, different types of routes. Actually, let's go ahead and take a look at router 5 first. Show IP route. And we can see that we do have some O routes, which are routes that we're learning inside of our area. Some OIA routes. There's a loop back on router 2, loop back on router 1, loop back on router 4, loop back on router 5, and so on. All right, plus the transit networks that fall between those routers. I'm not seeing any of the external routes. So let's go ahead and do a show run section router here and identify the processes that we're running. And I'm going to go into EIGRP 100. I'm going to say redistribute OSPF 1. So I'm going to redistribute the OSPF routes into EIGRP. I'm going to use a metric. Let's do a bandwidth of 1,000, a delay of 100 or 10, and then reliability of 255, 1, and 1,500 for load and MTU. All right, then I'm going to go into router OSPF 1. And I'm going to redistribute EIGRP 100 subnets. Now there's a lot of options that we have here. And again, when we get into our traffic engineering section, we'll take a lot closer look at this. You know, do I want to send these in as type 1s or type 2s? Do I want to send in only the type 7s? Do I want to apply some sort of per prefix application of metrics and route types and so on? Do I want to inject a default metric? We're going to go ahead and leave, or do I want to tag the routes? Most of these concepts have more to do with manipulating the redistribution process rather than actually influencing, you know, special area types. So we're going to go ahead and leave this right now just as the subnets coming in. So if I go back over to router 5 now, I should see those external routes coming in. Show IP route. And we should see, there we go. These are the external routes coming from our EIGRP domain. Now you see they're coming in as external type 2. They have a seed metric of 20, which is the default seed metric for routes that are redistributed into OSPF. Sorry about that. Close that out. All right. Not sure why that opened. Well, I clicked it, I guess. All right. So if I go into a show IP OSPF database, sure enough, I'm going to see my type 1 LSAs in the area. Router 2, router 3, and router 5 are all part of area 1. I'm going to see my type 2 LSAs. We could actually, in this particular topology, reduce those type 2 LSAs by making these point-to-point links rather than multi-access networks if I wanted to reduce the different LSA types within the area. And then I see my summary net link state. So we see our type 3s coming in that represent all the other nodes in the graph in other areas, and the prefixes we might be learning from those other nodes. Here are my type 4s. The summary ASB link state, which describes how to get to the ASBR, and then finally the 3 type 5s that are coming in from router 4 that represent those external prefixes that are being redistributed from EIGRP into OSPF. We have a question from Ken online. How do you determine what the seed metric should be when redistributing OSPF? We will talk about that later, Ken, but I can go ahead and kind of let you know. In the case where I have a single ASBR and it's originating routes individually by itself, there's really no need to either change the metric type or the seed metric, because we don't actually use the seed metric for those routes for reachability to the ASBR. We use the type 4 LSAs outside of the area to reach the ASBR. In fact, if I do a show, let me go back here, show IP OSPF database external, oops, show IP OSPF database external, I'm going to go back here, show IP OSPF database external, oops, show IP OSPF database external, show IP OSPF database external. you can see here that even though we see the metric type of 2, we see the seed metric, you think about this and you say, well, I don't really know how far away those routes really are, because the metric is the same in the entire autonomous system. But it doesn't really matter, right? Because if I do a show IP OSPF database and I look at the ASBR summaries, which are my type 4s, this indicates how far away the ASBR is from my location. Remember, I'm on router 5, so I'm basically trying to build my internal graph. I don't care about the graph of area 2. I don't really care about the graph of area 0. So router 5, from router 5's perspective, it's saying, the ASBR really knows how to get to the ABR in the area knows how to get to the ASBR. It's going to cost me 2 to get to the ABR. Okay, this is where it gets really, really complicated, because if I had multiple ABRs, I would choose to go to the closest ABR based on the type 4 LSA to leave my area. And then once I get into area 0, I would see a type 4 LSA on router 2, which should indicate that I have a couple of different options to get to that ASBR. In fact, let's go take a look at router 2 real quick. If I do a show IP OSPF database, show IP OSPF database, try that again, ASBR summary, we can see in this particular case, router 1 is advertising 4444, and router 6 is advertising 4444. So I get to kind of decide, and router 2 is advertising 4444 as well. I am router 2. So in this case, I get to decide, am I going to go to router 1 to get to that ASBR, or am I going to go to router 6 to get to that ASBR? And because the metric to reach the ABR that's advertising reachability to that ASBR is 1, that's the decision process. Am I going to go to this ABR? Am I going to go to that ABR? All right. So that is really what we're trying to use to get to this ASBR. Now, once I get into the area, once I get into area 2 in this particular topology, there are no type 4 LSAs in area 2 that represent the ASBR. So how is router 1 and router 6 deciding how to get to those external routes? If I go to router 1 and I do a show IP OSPF database, let me do the ASBR summary, right? We do see router 1 and router 6 advertising essentially those, kind of originating those summaries, those ASBR summaries, but we're not utilizing those ASBR summaries to reach router 4. In fact, if I do a show IP OSPF database, you will see that actually the router link states in area 2, we have 3 links that are being advertised by router 4 as type 1 LSAs by router 4 in the area. All right. Well, that makes sense. We've got the loopback, we've got this 14 subnet, we've got the 46 subnet. So I'm going to use these type 1 LSAs to identify what's the best way to get to router 4. And then I'm going to use the external LSAs, which I should see here. I think I stopped the output there. There we go. I'm going to use those external LSAs for reachability to these prefixes. So these are my type 5s that describe the 3 prefixes that are originating on router 4. This is where it gets, OSPF obviously gets a little bit more complicated than, say, EIGRP, right? And certainly RIP in this case, because we're trying to route to nodes. We're not trying to route to networks. Eventually, by getting to the node, we will be able to get to that network. But we are not trying to route to networks in the case of OSPF. We're trying to route to nodes. So to go back and answer your question, if I had in our topology here, I may add this for the next lesson here, but if I had router 4 and maybe a router 7, a router 8, a router 9, in area 2 that had reachability to these external links as well. Then I might decide, based on traffic engineering, which ASBR do I want to go to reach those external links. And that's when I would try to influence the seed metric and also influence the metric type. Because router 4 may be preferred, but I want router 8, for example, to be there as a backup, right? So let me kind of draw a diagram here. Let's say in this case, I had another ASBR here, and it had reachability to these 2 loopbacks. And maybe we're sending this into our area, some way or another. Maybe we even have multiple links to the 2 ABRs from the ASBR, okay? Well, now I have lots of redundancy. I have lots of options to reach those external networks. So how I decide to inject those routes, are they going to come in as an external type 1 or external type 2? What kind of seed metric am I going to implement? That will determine how I decide to route to those external networks. Okay? From the perspective of Area 1, it makes no difference. Area 1 is a stub area, essentially. Not by definition, we haven't configured it as a stub area, but it only has one way in and one way out. So it doesn't matter how we're learning about those external routes. We route to nodes, we don't route to networks. I'm going to send my traffic to the ABR, and then that ABR is then going to make a decision, do I send it to router 1 or router 6? And then router 1 and router 6 will make a decision, do I send it to router 4 or router 8? Okay? All right. So area 1, we're going to go ahead and configure as a stub area, and we're going to see what the effect is of area 1 as a stub area. Because area 2 has 2 ABRs, area 1 only has 1 ABR. Area 1 is really a great candidate to become a stub area. All right? Basically, it's the same thing as doing a summary from area 0 into area 1, summarizing in this direction, not this direction, okay? But in this case, we're simply summarizing down to the shortest match prefix, which is our default route. All right, so we've got redistribution running on router 4. All right, making this router now an ASBR because we're redistributing routes into OSPF. But before we can make any changes in filtering, and especially this would really apply when you guys are going into the exam, make sure everything is working, right? Especially for the configuration part. If they want you to create a special area type, maybe do some kind of special filtering, make sure the basic functionality is working. And we've already kind of verified that because we saw the external routes on router 5. So we check out the database on the routers, we break down the different LSAs based on what the topology looks like, and so on. In our particular case, router 2 is the only exit point out of area 1. So it's a great candidate for the stub feature. Just keep in mind, the stub flag is part of the OSPF negotiation. Make sure you make these changes, whenever you're creating these special area types, in a maintenance window, because it will disable your adjacencies between your peers. Okay? We will talk about all of the different options. So for example, if I come into router 2, and where'd my mouse go? Come on, mouse, where are you? It's weird, my mouse disappears every once in a while. There it is, I just saw it. All right, it's because it's a little dot when it's on the screen. I couldn't see the dang thing. So let's go ahead and go into router number 2 because that's the area border router in this case. We're going to go ahead and make area 1 a stub area to start with, okay? I'm going to do a couple of debugs. Debug IP OSPF adjacency and debug IP OSPF hello. And I'm going to go into router OSPF 1, all right? And I'm going to say area 1 stub. Now we have lots of options here, right? Well, 2 options actually. No external capability. Do not send domain-specific capabilities into the area. We'll talk about that when we get into the traffic engineering section. And then also have a choice of making this a totally stubby area by simply saying no-summary, which would suppress type 3s from going into the area. I'm just going to go ahead and make it a stub to start with. And you can see immediately we lose our adjacency with our peer, gets reset. Neighbor change event, we try to go through our reestablishment of our adjacencies here. And then I get this, let me do an undebug all. I get this warning or error that says, hello from router 3, 23.3 with a mismatched stub transit area option bit set. So in the actual hello packet, we are sending hellos with the stub area flag sent in the hellos. Let's see if we can see that in our Wireshark capture. So once I've established that one router in the area is going to be a stub, then all the routers in that area need to be configured with the same stub configuration. Very, very important concept. And you saw our adjacency went down immediately as soon as we did that. So let's see, we should be getting hellos being sent from router 2. This is the link between router 2 and 3. Router 2 is .2. And in our hello packet, I should see an indication that this is a stub configuration. Let me see, it's under extended maybe. Options. Let's see, why am I not seeing it here? Maybe it's in the header. Let's see, source, authentication none, hello packet. We are marking ourselves. I'm not seeing the stub flag. And I'm wondering if it would be in the updates. Let's see if it's in the updates. It really wouldn't be in the updates because we wouldn't be able to establish an adjacency anyway, which means we would never move beyond the two-way state. Let me do a show IP OSPF neighbor. And it looks like, yeah, so we're down and that's it. So we haven't even reached the two-way state in this particular case. I thought, though, that we would see in the hello packet an indication that the stub flag is set. Let's see here. Option, no, no, no. Well, we can always use our trusty Google stub flag in OSPF. Stub area must be a stub routers. The flag indicates. So exchanging hello packets with a flag that indicates the interface is part of a stub area. That's what I thought, but I'm not seeing that flag specifically, and I'm wondering if it's kind of hidden in another option here. Certainly the area ID, so that's area 1, router 2, hello packet. You would think it would be under options here, but in any event, we're not seeing it in Wireshark, but it's definitely there, and it definitely has to match on all the routers in the area in order for us to be able to move beyond the down state. So let me go ahead and go into router 3 and router 5, and we'll go ahead and set the stub configuration on router 3 and router 5. Let's just do it this way. Config T, router OSPF 1, area 1 stub. Okay, and we'll send that over to router 3 and router 6. Okay, config T, area 1 stub. All right. So that should then allow us to form our adjacency between router 3 and router 1 again. Make sure I did the right routers. Yep, router 3, and I did router 6. I meant to do router 5. See, that's what I get for trying to be fancy with this stupid command line. Config T, router OSPF 1, no area 1 stub. Not that that would have affected anything on router 6, because router 6 is not part of area 1. We need to do this on router 5. Router OSPF 1, area 1 stub. What I meant to show you, actually, we did kind of already look at this back here. This was our original routing table. All right. When we were basically just a normal router, we had no gateway of last resort, no default route. We had our OIA routes, and we had these 3 external routes. Now that this area is a stub area, we of course would expect to see something completely different. Show IP route, we have a gateway of last resort, which is set to router 3. Remember, router 3 in this topology is this router. If I was to look in router 3, it would indicate that the next hop is router 2. All right. So that's being injected. That's coming in as a type 3 LSA. And we can see that the external LSAs have been basically suppressed. So if I do a show IP route, let's look at 100.0. We don't have a route in that routing table, but if I do a show IP ceph, 192.168.100.1, I can see that I am going to send that out to router 3. And if I go to router 3, show IP route, 192.168.100.0, no route. Show IP ceph, 192.168.100.1. I'm going to send that over to router 2. All right. So this is our special area type, stub area. Just to confirm the configuration, show IP or show run section router. We can see it was one single configuration, area 1 stub. Okay, and I would do that on all the routers that are part of the area. So the default route comes in as a type 3. We have no more type 4s or type 5s in this area. We still have a default route. We lose visibility to the ABRs. We also lose specific visibility to the external networks, but reachability is not affected. Okay? Area 2 is a little bit more complicated because if we lose availability and we have 2 ABRs, it's just the overall configuration is a little bit more complicated. I'm going to get into that one in a little bit, but for now let's focus on this area here. Okay? Now what changes if I want to make this area totally stubby? Remember, totally stubby, if I go back to router 5, would suppress not only the type 5s coming in, but it would also suppress all of these OIA routes coming in. Basically, all I have to do is on this ABR here, is I have to add a keyword to my configuration. Router OSPF 1, area 1 stub, no-summary. Which makes sense, right? I mean, what type of LSA are we trying to suppress in addition to the type 5s and type 4s that would normally come into this area? We're trying to suppress our type 3s. And by definition, what is the name of a type 3? It is called a summary LSA. So if we say no summary, logically that makes sense that we're avoiding the influx of those summary LSAs into the area. All right, and that's our goal in this case. So quite easily we can go ahead and verify that that's actually happening by going back to router 5, doing a show IP route, and we can see that we actually lose all of the OIA routes, and the only route that we see injected is, which is kind of interesting, is an OIA route which is technically a type 3, representing that default route that's being injected automatically by the ABR. So if I do a show IP OSPF database, even though technically summary LSAs are not allowed in the area, we're still injecting the default route as a type 3. This would be completely different than if you did like a default information originate on one of the other routers in the other areas, because default information originate is kind of like sending in, well, it isn't kind of, it's exactly like sending in an external route, redistributing a default route into OSPF, which is absolutely not allowed in the special area type. Okay, so now we only see our type 1 LSAs in the area. We only see our type 2 LSAs in the area. If I did the same thing, show IP route, show IP Ceph, we would essentially have a situation where we would have, you know, no route, but it would still be reachable in the forwarding information base because we're using the default route to reach that destination. So let's go ahead and make router 2 an ASBR. Okay, I'm going to do this for a specific reason. All right, if I go back to my diagram here, I want to make router 2. We'll get over to the left side of this later on in the last half or last third of our discussion here. But I'm going to go ahead and make router 2 an ASBR. Now, what's interesting about this concept, it's already an ABR, right? We know that because it's joining area 0 to area 1. But I can make router 2 an ASBR even though it's not, it's kind of technically in a special area type. The reason we can make it an ASBR is because it's part of area 0. So I'm going to create a loopback on router 2, and we'll just create some basic loopback on router 2. Where did my mouse go again? All right, here we go. And we'll make it very unique here. So config T, interface loopback 100, IP address 55.55. Now let's do 99.99.99.99. 255.255.255.255. And I'm going to go into router OSPF 1, and I'm going to do a redistribute connected. Okay? And that will take that 99.99.99.99 loopback, and it will send it into OSPF. In fact, if I go all the way over to, in our topology here, go all the way over to router 4, I should see that route in my routing table. Do show IP route, and sure enough, I see 99.99.99, and it's coming in as an OE2 route. I can equally load balance using equal cost or ECMP, multipath routing, between router 6 and router 1 to reach that destination. But if I go to router 5, which is in the special area type, and I do a show IP route, I still don't see the 99.99.99.99. But if I do a ping to 99.99.99.99, I have reachability. Because again, we're using that default route to reach that destination. So now we've got type 5s that are kind of going back and forth in this topology. Of course, the type 5s are not going to be allowed into area 1 because of its special area status, but we are able to see that on the rest of the network. Okay? What if I tried to create a loopback on router 5? And I'll do 100.100.100.100, 255, 255, 255, 255. And I went into router OSPF 1 and I did redistribute connected. It's going to give me an error, right? It takes the command, but it says the router is currently an ASBR while only having one area, which is a stub area. You're not allowed to have an ASBR in either a stub area or a totally stubby area. So let's go make sure that in fact that route is not going to be sent into router 2, show IP OSPF database. I don't see the type 5 LSA for 100, 100, 100, 100, but do I still have node reachability to router 5? And it looks like in this particular case, I lost node reachability to router 5. Let me see here. because router 5 should be definitely in area 1. Oh, that's area 0. Let's go look at area 1. Show IP. Let's do this. Show IP OSPF database router. Okay. Let's just do database. I want to look at area 1 real quick. So I still have reachability. I'm still getting the 2 links from router 5, which makes sense. That's the loopback and the LAN, the transit network on router 5. So I still have reachability to router 5. It's just suppressing the injection of that external route that's being redistributed because it's not allowed. Router 5 is an ASBR, and it's not allowed in a special area type. Okay? So that brings us to our third and final portion of this particular lesson, which is how do we do traffic engineering with stub areas? In our next lesson, we'll talk about NSSA in more detail. We'll talk about totally NSSA in more detail. Right now, we're going to focus on what happens when I have multiple ABRs in a stub area. Okay? In the case where we have multiple ABRs, it does get a little bit more complicated, especially with special area types. OSPF stub areas that have multiple ABRs have multiple exit points. And we have a couple of options when it comes to traffic engineering in and out of these stub areas, which can either be based on longest match routing or something called the area default cost. Looking at our topology here, we see that in this particular area, because now we're going to shift our focus over to this area here, right? We get rid of that line. We're going to shift our focus over to this area here and focus on what happens when we want to route in and out of that area, and at the same time making that a special area type. Area 2 has 2 ABRs. So the first thing I want to do is I'm going to go ahead and just remove the redistribution because we want to set up area 2 as a stub area. When we get into our next lesson, we'll talk about NSSA and totally NSSA. So for now, I'm just going to go ahead and kind of remove the redistribution on router 4. Do show run pipe section router. We'll reintroduce that concept when we get into our next lesson. So router EIGRP 100, no redistribution, OSPF, and router OSPF 1, no redistribution EIGRP. So we no longer have an ASBR in the area. We just have basic routing concepts. And again, if I do a show IP route, this is a kind of a basic normal area. I've got no gateway of last resort. I've got my type 3 LSAs. I've got my type 5 coming in from the loopback on router 2. And I've got my type 1s in the area. Where are my type 1s? I guess all my type 1s are connected routes, so they're not showing up as connected. I should have at least one type 1, though. Let's see. Let me look at my topology diagram. Nope, that's right. These loopbacks are in area 0. I was thinking that I had one of these loopbacks in area 1 or area 2. So yeah, I'm not going to see any type 1s because these are directly connected routes. I would see them in the database as type 1s, but I'm not going to see in the routing table as type 1s. Okay, so we're going to take a look at what is longest match routing to leave the area versus area default cost. Let's go ahead and make all the routers in the area a stub. I'm going to try and do this again. All right. And in this case, we're focusing our attention on router 1, router 6, and router 4 for area 2. So router 1, router 6, and router 4. Router 1, router 6, and router 4. And we're just going to do let's get rid of that. That's good. Router 1, router 6, and router 4. Okay. Config T, router OSPF 1, area 2 stub, and right. Okay. All right. So that should have worked. Okay. And sure enough, if I go to router 4, because router 4 area, this area is a stub, I should now see a default route being injected, which is coming from router 6. That's an interesting concept. Why router 6? Why not router, why did we choose router 6 over router 1? We have equal cost paths here between 6 and 1. Well, there's that election process. And incidentally, in OSPF, it has very much to do with the same thing that we do any kind of election in OSPF, router ID. All right? So in the case of router 1, or excuse me, router 4, it is choosing to go to router 6 to reach that destination. If I do a show IP route, 0.0.0.0, I can see that actually in this case, it looks like it's going to try to load balance. I guess because we can only have one entry there. That's what it's representing there. So it looks like in the case of, let's do a trace route to 5.5.5.5. Yep, so it is going to 1 and 6 and 1. So it is load balancing across those two peers. All right. But for some reason it put 6 in here first. And it only shows router 6 as the next hop for the default route. But always check, yeah, right? Check the routing table details to find out whether or not you are choosing one path over the other. Okay, and in this case we can clearly see that we're definitely load balancing between the two pairs, two routers. That's actually what the whole point of this part of the discussion is how do I influence that? How do I choose one versus the other? Okay. All right. So we don't see type 4 LSAs anymore. We don't see type 5 LSAs. But again, this is where the stub configuration and the stub design becomes more complicated. All right. So let's start our traffic engineering discussion by making a decision on changing the metric of the injected default route. If I did, like I said, a show IP route for 0000, which you see on the screen here, for router 4, we could see that it's going to load balance. And there's a couple ways you can test this. If I do show IP Ceph, for example, exact route, and we'll go to 5.5.5.5, which is router 5, a source port of 1, 2, 3, 4, 5. Actually, let's source the traffic from 4.4.4.4 and a source port of 1, 2, 3, 4, 5. And we'll do a destination of 5.5.5.5 with a destination port of 80. We can see that it's going to send that traffic to 4.6. Now, if I change this port, we might have to change a couple of variables here. Yeah, it depends on what kind of load balancing we're doing with Ceph, but we're not seeing any changes here. Eventually, we may see a change, but the trace route also demonstrates that if I did for example, a no IP Ceph, config T, no IP Ceph, or I changed the Ceph load balancing option. Well, I can't show you now. Anyway, you get the idea. The trace route certainly showed that. So it show IP Ceph load balance. I think it's load balance. Show Ceph. Switching, no. It's escaping me right now, but very basic command. But anyway, we know based on the trace route that we're definitely using both gateways. Okay, so let's say in this case we wanted the traffic to go in only one direction. If I do a show IP route 0.0.0.0, we can see that the metric to reach this gateway is 2. The metric to reach this gateway is 2. So, and if I go ahead and try and influence that to decide or to put, let's say we wanted to, in this case, force all of our default traffic to use router 6 instead of router 1. Maybe router 1 is a backup, so we want to send all of our default traffic this way. We can simply change the cost of this link right here on router 1. If I go into router 1 and config T, interface GI01, IP OSPF cost 1,000. Now if I go back to router 4, I can see here that we have to wait for some convergence here. We should see the cost change. Did I do the right interface? Or did I do the right router? Router 1, gig 01. Okay. Show show IP interface, show IP OSPF interface GI01. Cost is 1,000. And if I go to router 4, it's still showing them with an equal cost. And I'm trying to think why it's doing that, because the cost is definitely cumulative. And I'm wondering if it's based on ingress versus egress. Let's go. Yeah, it is. I got to go the other direction, because cost to a destination is always based on egress, right? Not ingress. So I'm not advertising a cost to that destination. I need to calculate the cost to that destination. So I need to change gig 01 on router 4. All right. Config T, interface GI01, IP OSPF cost 1,000. So IP route 0.0.0.0, and it changed. Okay. So we see now that in this case, we're no longer load balancing to the destination. Remember, when it comes to metric calculations, it's always based on egress, not ingress. I was looking at it from the perspective of router 1, but I really should be looking at it from the perspective of router 4. So now if I come into interface GI01 and I shut that down, do show IP route, we will still see that we actually have a default route. Let's do show IP route 0.0.0.0. But that route, I shut down the wrong one. Hold on, no shut. Let's shut down the one that we're actually using, which is going to be gig 00 in this case. Interface GI00, shut that down. And do show IP route 0.0.0.0. Now we see that, we should see that we're going to send our default traffic over to router 1. All right. And we could do other things, like that was a relatively quick, if we were doing BFD or something like that. We didn't need BFD in this case because it's a point-to-point link, so the link state went down. We recognized that right away. But you could potentially add BFD if you wanted to change the convergence and the switch over to sub-second intervals. So we're definitely using the other route. All right. So we know that in this case now, our default traffic is preferring to leave the domain in this direction. Okay. Because we increased the cost of this link. Here's the problem though. We also increased the cost of that link for everything else that we're learning from router 1. All of those type 3s potentially type 5s, in this case type 3s because this is a stub area, are being influenced by this decision process as well. If I did a show IP route for my OAA routes, you would see they're all going to router 6 as well because of the overall path cost. If I go into interface GI00 and I shut it down and I do a show IP route, now all those type 3s are going to come in and they're going to be learned from router 1 but that wasn't my original intent. My original intent was to affect how the default route was being sent in. So let's do a no-shut. Let's go into interface gig 01, and let's come up with a better way of influencing how the default route is injected into the area based on our stub configuration. So let's do no IP OSPF cost. Let's go ahead and remove that on router 1 to show run interface GI01, I think it is. Yeah. Not that this affects it at all, but I'd like to keep this clean. No IP OSPF cost. Now, there is a way that we can identify how we reach those border routers. Now that I've cleaned it up, if I do a show IP OSPF border routers, I can see that the cost to reach this border router is 2. The cost to reach that border router is 2. Had I looked at that prior to making the change, the SPF costs are no longer going to be equal, and we would be using the path that had the lower cost. All right, now that we've removed that, though, we have equal cost matches again, and I'd rather change how the routing is done without affecting other routes that are being sent in the area, and also without affecting the type 1 LSAs that are being learned from router 1 and router 6 as well, because that we didn't really have any specific type 1s that weren't already connected to router 4, but if we did, it would have affected all those routes as well. So again, let's go ahead and make router 1 the less preferred route. What we're going to do is we're going to go into the OSPF process, router OSPF 1, and we're going to say area 2, which is the area that we're sending the default route into, and we're going to set the default cost to some value. And notice that this only applies to stub advertised external route metrics. It does not apply to other metrics for other routes that are being sent. Okay, so let's make that 1,000. Now if I go back to router 4, I look at the cost to reach the border routers in the area, it's still a cost of 2, which makes sense because we're not influencing how we get to the ABR in this case. We're influencing what the default route looks like. So if I do a show IP route, I should see that my default route points to router 6 with a cost of 2. That's on gig 00. So if I go into interface GI00 and I shut that down, wait for some convergence, show IP route, I should see that we switch over to router 1 and we have a cost of 1001. So in this case, by injecting or changing the default cost, we affected how we route from a default route perspective, but we have not affected how we route based on the other prefixes that we're learning about. Okay, so if I do a show IP route pipe include OIA, we can see that, well, in this case, let's do a no shut. Obviously, we're running over router 1, but you can see the metric there is not affected, right? We still have kind of just the regular path metrics that we normally would see for those destination prefixes. All right. So we're going to router 6. We're going to router 6. Some of them are router 1. And again, we're making a decision on how to leave the area based on certain criteria. If I do a show IP route 5.5.5.5, you can see that we have 2 options to leave that area. And if I do a trace route to 5.5.5.5, you can see that we are load balancing. Router 1, router 6, router 1. And if I run it again, it should be router 616, router 1, 6, 1, 161, 161. So we're clearly load balancing to reach those destinations. All right. And that's based on our internal cost to reach those ABRs. The key thing to understand here is if I do a show IP OSPF database, we need to make sure, let's do show IP OSPF database router. We need to make sure that these LSAs are routable, right? And we're looking for the routing bit. We could look in the updates if we wanted to see the routing bit to indicate that we can route to those destinations. Just because we have visibility to the nodes does not mean we have reachability to the networks. So if the routing bit is not set, we will not be able to install that route in the routing information base or the forwarding information base, and we will not be able to forward to those destinations. All right? Now, what if I want to choose the best path for the other types of routes? I was thinking about what I wanted to do to wrap up today's lesson. We still got a little bit to go here, but we're getting close to the end for you guys that have some other things to do, but hopefully you're enjoying this conversation so far. What if I wanted to choose a path based on the types of routes, right? So we know that we're sending in type 3s, but I want, let's say, for example, based on what we have configured now, okay? Let's say in this example, for this for the loopback that we created here, that 99 loopback we created there, I want to choose this path to reach that 99 prefix. But I'd rather go this way for this 35 prefix. All right? We already saw that we're actually load balancing to get to that destination. And we already saw when we did our show IP OSPF border routers that we have the same cost to reach the ABRs. Now we could, again, set the cost on one router to a higher value, and then those inter-area routes are basically going to route to the shortest path cost for the inter-area routes. But you're not allowed to really change this on a per prefix basis. It's going to affect all of your inter-area routes. The best way to do this would be to do something based on longest match. Again, this is going to apply essentially to all prefixes. We would have to do some very specific traffic engineering if we wanted to manipulate metrics and whatnot for specific types of routes, and that's really beyond what we're trying to accomplish here. But there's actually a very simple way to send the 35 network traffic to router 1 and all the 99 traffic to router 6. It's probably not the best option, but for now it's what we're going to do. Okay? You could do something with distribute list filtering or LSA type 3 filtering, and maybe we'll get into that a little bit later on when we get into our traffic engineering section. But what if I just suppressed type 3s on router 6? And I said, you know what? I don't want router 6 to send any type 3s in. I want all the type 3s to come in from router 1. It's actually a very simple configuration. Go to router 6, config T, router OSPF 1, and area 2 stub, no summary. Oops. So now router 6 is no longer sending in type 3s into area 2. And if I go to router 4 and I do a trace route to 192.168.35.5, I can see I'm no longer load balancing. I'm going to router 1, router 2, router 3, router 5. If I do a show IP OSPF database summary, I can see, let's just do database. I can see that I'm only getting summaries from router 1. All right, now there is a summary default coming in because it is a stub router, so it's still sending in that default route. But as far as all the other prefixes that are coming in, those are only coming in from router 1. So by just suppressing the summaries on router 6, I've influenced all of that inter-area routing to go to router 1, as opposed to both router 1 and router 6. This could very easily be something that you guys would have to configure in the lab on your exam as well. You know, they're going to have you do things kind of in different ways. All right? So we're suppressing summary routes on the ABR, which is the opposite of the default route path with the no summary keyword. So only now one ABR is advertising those specific routes and longest routing applies here. Not that we don't have reachability, right? If we were doing LSA type 3 filtering or we were doing some sort of distribute list filtering, the issue we would have with the filtering is if we lose reachability, then we would lose the redundancy in our network. We would not be able to route to that destination. With stub areas, we can determine which router handles which types of routes based on different options. On one router, we made the default cost higher. The other router, we suppressed the summary inter-area routes by using the no summary. So I'm going to do one last thing here just to verify. I mentioned BFD. It's not really something we need in this topology here, but I'll go ahead and we'll do a configuration, a BFD configuration, and just verify that we do have reachability to the destination here. So I'm going to configure BFD between router 1 and router 4. Config T, show, let me see, do show IP interface brief. That's going to be gig 00, interface GI 00. Let's just do this together. And it's going to be router 1 and router 4. All right, config T, interface GI 00. And we're going to do a BFD interval. Let's do 50 with a min RX of 150 and a multiplier of 3. And we'll go into router OSPF 1. And let's do BFD on all interfaces. We could just enable it on that one, but since we only have it configured on that one. And let's do a write, save our config. All right. All right, so now if I do a show BFD neighbors, I can see, ooh, it's down, 46.6, should be router 1 and router 4, gig 01. Did I do it on the wrong interface? I did, dang it. All right, let's try that again. Interface gig 01, and let's just do, since we have it here, and go to router 1, interface gig 01. Oh, I didn't get it at all in router 1. Ah, that's why. Didn't take my config T. All right, no big deal. See, I try to get fancy with that stupid scripting thing, and it just takes me more time. Thank goodness that's not available in the lab. All right. Let's do BFD all interfaces. Show BFD neighbors. All right, there we go. And let's do show BFD neighbor detail. So we can see that it's running for OSPF. All right. Now, again, in this case, it doesn't really make a whole lot of sense. You know, obviously, in our topology here, BFD is not really going to save us a lot, because we've got direct link status between the routers. But if this was a multi-access network and there was some switch or some layer 2 data plane in between those links, then we would have to wait for our dead timer to expire in order for us to effectively identify that that route is no longer available. So if I go to router 1, interface GI01, and I shut down that interface, obviously, the whole point here is that router 4 should be able to route to 5555. We don't see I thought router 6 we were doing the no summary. Show run section router. Yeah, router 6 we're doing the no summary. Maybe I just didn't give it enough time, because we shouldn't see the OIA routes. There we go. I didn't give it enough time to converge there, but I should still be able to ping 5555 because, again, we have reachability with the default route. Okay, so there's all kinds of interesting things that you can do with the configuration here. This is just the beginning. In our next lesson, let's just kind of cover what we covered here. We talked about, in this case, what is a stub area, what are the different types of stub areas that we have in OSPF. We talked about how do I configure my stub areas, and we didn't look at NSSA or totally NSSA just yet. We're going to take a look at that in these three sections here. Controlling NSSA redistribution. That's going to be how we send routes into S-type 7s into the area, which will also really kind of apply to how do we control routes that are coming in from a ASBR in a normal area. We control them essentially the same way. We talked about the configuration of stub areas specifically related to the stub and the totally stubby configuration. And then we also talked about traffic engineering with OSPF stub areas, identifying how we could influence the default route that's being injected, and so on. Now, in our next lesson, when we get into NSSA, we know a default route does not get sent in automatically, so how do we handle that issue? What is the process of doing redistribution in a not-so-stubby area? And how do I control that? How do I set the seed metric? How do I set the OSPF type, external type, whether it's 1 or 2? What is an ON route versus an OE route, and so on? All right? So do you guys have any questions before we wrap up for today? I'm going to go ahead and save the stub lesson here. And we'll put that into our CCIE. Routing topics. Stub areas. And stub notes. All right. I'll upload the video as well. All right. So see you guys in the next lesson.